All machines, no matter what they are, obey the laws of physics. There are many applications and many types of industry that we may come across. However, no matter how different or complex that they may appear to be, we can take comfort in knowing that they all obey Newton's laws of motion. Even non-self-excited applications such as structures and machines that involve linear motion rather than rotary motion obey the same laws. The law that's of most interest to us is Newton's second law of physics, which says that force equals mass times acceleration. As a simple experiment, here to illustrate this point, we have a machine in the form of a bench-top grinder sitting on top of a set of bathroom scales. The grinder weighs about 5 kilograms, so we get a reading because the force of gravity is pulling the grinder down onto the bathroom scales, giving us a reading of its static mass. No matter how well the machine is constructed, there will inevitably be some residual unbalance in the rotor. Even a gyroscope, which is very finely balanced, will have some degree of residual unbalance. The position of this rotor's heavy spot is indicated by the red arrow. When the rotor is at rest, this unbalance has no effect. When we switch on the motor, the unbalance generates a centrifugal force, which changes in direction as indicated here by the rotating arrow or vector. Our bathroom scales are measuring force in just one place, the vertical plane, and will respond to the effect of this centrifugal force. When the centrifugal force acts in an upward direction, the reading on the scales will decrease, and when the centrifugal force acts in a downward direction, the force reading on the scales will increase. If we were to plot the forces going into the foundation of our machine, as indicated here by the bathroom scales, then as the vector rotates through 360 degrees, we would generate a sine wave. In the real world, of course, it's impractical to install scales or some kind of force sensors under the feet of a machine in order to measure the effects of these forces. This would be expensive and invasive. A more practical way to study these forces and resulting motion is to use an accelerometer, which we can position on top of the machine. This is a device which measures, as its name implies, acceleration. It contains a piezoelectric crystal which creates a voltage as it moves up and down. We can capture this signal by connecting the accelerometer to an instrument. So if we look on our instrument at what happens as the vector rotates, we see a sinusoidal waveform representing the effect of the forces acting upon the machine. It is the forces acting upon a machine that are the cause of vibration. Vibration is not a cause of a problem, it is a symptom. If there are any mechanical tolerances in the build of a machine that allow movement, then resulting movement will correspond to the amount and direction of the force that is being applied. If, for example, the machine is not bolted tightly to its foundation, then, as the machine rotates, the resulting motion can be measured using an accelerometer. There is a direct relationship between the force that's being applied and the corresponding vibration that it generates. To reduce the vibration on a machine, the best approach is to reduce the forces that generate it. So if the machine is out of balance, then improving the balance condition will reduce the forces and reduce the vibration pro rata. The value of the vibration will be proportional to the amount of work that's being done by a machine. Logically, a small, low-powered machine will develop lower forces than a bigger, high-powered machine. In consequence, the generated vibration will be less. A bigger machine has typically more power, and hence we would expect to see higher levels of vibration. Another thing that needs to be taken into account is load. The harder the machine is working, the more current it's going to draw. There's more work being done, so the levels can be expected to go up. An analogy: driving a car on a flat road. When you start to go uphill, you can hear the engine working harder, and very often you can feel the vibration levels in the vehicle increase. The reason why we do all of this is to detect machine faults. We have already mentioned unbalance. If your machine is faulty, then we can use vibration to detect that fault. If you're in the business of manufacturing machines, then you can use vibration as a reflection of the quality of the machine before shipping it to your customer. Then, after the machine is installed at the customer's site, you can observe how the vibration deteriorates with time, and that's called machinery condition monitoring or predictive maintenance. We need now to look at the units of vibration measurement and other associated terminology. So mechanical structures, when excited, will tend to vibrate with sinusoidal motion. So to understand vibration, we need to understand the quantifying parameters of sine waves. In the previous module, our machine structure was a bench grinder sitting on top of a set of bathroom scales. Like all machines, that structure had mass, m, and stiffness, k, which can be represented by means of the mass spring system shown here. The motion of the mass from one extreme of displacement to the other extreme, and then back to the start point, is referred to as one cycle of motion. The time, t, taken to achieve that cycle is referred to as the period of the motion. In machinery terms, this is typically a very small value and difficult to relate to other aspects of the machine's operation. Instead, we consider the number of cycles that are achieved in a For a sinusoidal motion, there is a mathematical relationship between the three amplitude parameters. Given one, and knowing the frequency of oscillation, then it's easy to calculate the others. If we use an accelerometer sensor, then we directly measure the acceleration level. Dividing that figure by 2 pi f gives us the velocity of the vibration. If we take the acceleration level and divide by 4 pi squared f squared, then we get the displacement value. However, you need not be concerned about the mathematics involved. Most analyzers and vibration meters will do the maths for you. You simply tell the instrument what type of sensor you're using, what parameter you want to see on the y-axis, and the instrument will do the arithmetic. All you need to do is hit the required switch. In practical terms, this also means that using one transducer, such as an accelerometer, can be used to measure all three parameters. However, even though this is a very basic introduction to vibration, one thing that you need to be aware of is the effect that doing this arithmetic has on the signal. In previous displays, we saw how the signal varied against time. When we look at the signal in that way, we speak of the time domain. The display shows the vibration velocity level on the vertical axis, plotted against the vibration frequency on the horizontal axis. This is commonly referred to as a vibration spectrum. Some people also refer to this as a vibration signature. When we view the signal in this way, we speak of the frequency domain. We will return to this way of looking at vibration data in more detail when we reach the Diagnostics module. For now, we see a vibration velocity reading taken from a stationary machine. Note that even though the machine is not running, the instrument is suggesting that a vibration level of 2.16 mm per second is present. We see that all of the indicated vibration occurs at the bottom of the frequency range. This is likely ground-borne vibration. In the real world, it's common that vibration from other sources, for example adjacent machinery, or even traffic moving along a nearby road, or trains moving along a nearby track, is transmitted through the ground and is detected on by the sensor on the stationary machine. This seismic vibration, as it is sometimes known, tends to be always present and is typically low frequency in nature. If a high amplitude of vibration velocity low frequency is observed, then the most common reason is an amplification of the data caused by the process of high amplitude of vibration velocity low frequency is observed, then the most common reason is an amplification of the data caused by the process of integration from acceleration to velocity. The spectrum shown here depicts the vibration acceleration as measured directly by the accelerometer sensor. To convert the spectrum from g versus frequency to millimeters per second versus frequency, we divide each value of g in the spectrum by 2 times pi times f as explained earlier. On the left of the spectrum, f is a low number. Divide a low number into a bigger number and you get an even larger number. So when we look at the same signal in terms of the calculated velocity level, it appears that the low-frequency peak is much larger. This effect is exacerbated if we divide the acceleration values by 4 times pi times f squared to view the vibration in terms of its displacement. The effect is commonly referred to as the ski slope. Causes of low-frequency signals in the vibration spectrum are A. It is a real signal, that is, low-frequency vibration is actually present. B. It is a false signal caused by instrumentation faults, for example, poor screening, poor contacts, incorrect selection of an appropriate transducer. C. Electrical noise generated by the sensor's inbuilt electronics. This is sometimes referred to as ICP noise. ICP stands for Integrated Circuit Piezoelectric Sensor. Item C is the most common. Some accelerometers will emit a signal at 1 Hz or below, which is due to the ICP circuitry. When converting from acceleration to velocity, this signal gets amplified and values of 360 mm per second or even higher may be observed on the y-axis. To combat this, you can install a low-frequency filter. The ISO committees responsible for compiling machinery vibration standards are obviously aware of this issue, and most specify that readings below 10 Hz should be disregarded. Be aware, though, that some standards specify 2 Hz. The electronics of most modern vibration instruments therefore typically offer appropriate switchable filters. To study real low-frequency vibration, it is necessary to use a special accelerometer which is designed for the purpose and which does not emit ICP noise at low frequency, for example SKF sensors shown here. In the previous module, we learned that there are 3 measures of vibration amplitude: displacement, the distance through which the mass moves; velocity, the speed at which the mass moves; acceleration, the rate at which the velocity changes. We also saw that each of these parameters varies sinusoidally during each cycle of vibration. So how can we express the value of a signal that is constantly changing? 1. The total signal value from one extreme to the other extreme is called peak to peak, pk to pk. If the peak-to-peak amplitude is not constant, that is, changing with time, we usually record the value when it was at its biggest or maximum. 2. The signal value from point of rest or reference position to one side only is the peak value. 3. Most ISO and European standards will require you to measure the signal's root mean squared value, RMS. The RMS value is the most commonly used way of expressing the value. It's a way of averaging the signal, so let's take a little time to understand it in more detail. The RMS value is calculated by taking a series of amplitude measurements over a period of time. For example, 1024 measurements over 400 milliseconds. The simple average, or mean value of these measurements would be 0, because for half of the cycle the values are positive, and for the other half of the cycle they are negative. Square each value and then take the average or mean. When the negative values are squared, they become positive values. Take the square root of the mean value and that gives the RMS. The signal is measured over a period of time, and so the RMS value is proportional to the amount of work being done by the machine or to the amount of fault energy. Note that average measurements are often preferred by the gas turbine industry, and this is simply 0.9 of the RMS. So there are 4 ways of measuring the amplitude values. 1. Peak to peak. 2. Peak. 3. RMS. 4. Average or mean. This becomes important when we wish to compare vibration data with some published standard, or if we wish to compare vibration data taken with different instruments. In such circumstances, it is obviously important to compare like with like. In fact, if we assume that the motion is sinusoidal, then there is a simple arithmetic relationship between all four quantifiers. For example, the peak value is root 2 times the RMS. So far we have considered vibration as a simple sinusoidal motion occurring at only one frequency. Vibration from real machinery is usually more complex, involving motion resulting from a combination of forces associated with different machinery faults. Consider the machine train shown here. If the accelerometer is placed at, say, the gearbox input bearing, then what is being sensed? The vibration at that point will represent the total effect of all the forces present in the machine as transmitted to that point. There will undoubtedly be some vibration present due to unbalance in the drive motor. It may not represent a problem, but it will be present. This vibration results from the centrifugal force induced by the unbalance. The frequency of that vibration will therefore equate to the rotating speed of the motor. That is, if the motor is rotating at 1500 RPM, then the vibration frequency will be 1500 CPM or 25 Hz. There will probably be some vibration resulting from misalignment in the coupling. Again, this may not represent a problem, but it will still be present. Vibration resulting from misalignment will logically occur at a frequency relating to the RPM of the offending shaft. Depending upon the nature and severity of the condition, it may occur at various multiples or harmonics of the shaft speed. For the purpose of this exercise, let us imagine that the vibration occurs at 2 times shaft speed frequency. There is likely to be some vibration present as a result of the meshing action of the gears. The gear mesh frequency is the number of teeth on the gear multiplied by its RPM, so this will be higher frequency than the other vibration components considered so far. There may well be other vibration components present, but for the purpose of this exercise, these will be ignored. The total vibration sensed at the gearbox input bearing will be the total of the various components present. Adding together vibrations of differing amplitudes at different frequencies does not result in a new, simple sinusoidal waveform. The combination of these different vibration sources results in a more complex time waveform, the characteristics of which will be dictated by the individual vibrations present. This total vibration is referred to as overall vibration, sometimes called broadband vibration. This overall vibration can still be expressed in terms of its peak value, peak-to-peak value, RMS value, average or mean value. A lot of condition monitoring activity relies on periodic or continuous measurements of the overall vibration level. Indeed, ISO standard 108163 defines areas of vibration severity according to overall levels of vibration velocity. This approach to condition monitoring has the advantage that it can be applied with relatively simple, inexpensive instruments and systems, and it works on the basis that if the total vibration does not change, then it's a reasonable assumption that the individual vibration components have stayed the same. So when the total vibration increases, then these basic measurements give warning of an impending problem, but typically lack the ability to identify the particular component of vibration that has deteriorated. This requires instrumentation that provides information regarding the individual vibration frequency components that are present. We shall discuss this in more detail later in this course. We learned earlier that we can express the value or amount of vibration in terms of displacement, the distance through which the mass moves, velocity, the speed at which the mass moves, acceleration, the rate at which the velocity changes. So which of these parameters should we use when attempting to monitor change in machinery condition? ISO standards are available to guide you in this, but if you don't have guidance from a standard, then you'll need to choose your own, so consider the following. We also learned that there is a mathematical relationship between the 3 parameters. Velocity varies with the frequency, whilst acceleration varies with the square of the frequency. Here we see the relationship between the 3 parameters expressed graphically. For a constant displacement, we can see the resulting velocity and acceleration levels at various frequencies. It's evident that at high frequencies, relatively low levels of displacement can result in high levels of acceleration, because acceleration is a function of displacement and the square of the frequency. Newton's law tells us that force equals mass times acceleration. This means that at high frequencies, even moderate excursions can result in the generation of very destructive forces. Therefore, if we are measuring high-speed machinery or machines which can generate high-frequency vibrations, more than 10 kHz, then acceleration is a meaningful parameter to measure. Conversely, at low frequency, even relatively high levels of displacement will result in low levels of acceleration. Here the problem is not one of force, but rather one of stress. Components may suffer degradation as a result of stresses induced by deflecting them through too great a distance. So where low-frequency vibrations, below 10 Hz, are of concern, displacement is a meaningful parameter to measure. Fatigue failures occur when components are subjected to repetitive cyclic stresses. The time taken to reach failure is typically a function of the deflection that occurs, that is displacement, and the rate at which the deflections occur, the frequency. As we saw a few moments ago, velocity is a function of displacement and frequency, so for general machinery use, where fatigue failures are of concern, velocity is a meaningful parameter to measure. Impulsive signals result from impacts. As an example, consider what happens if we use a screwdriver handle to tap this bench grinder as we collect vibration data using an accelerometer mounted on one of the bearings, as shown. Here we see the resulting time waveform. During the time taken to collect this data, the machine was struck twice with the screwdriver handle. We can see the two spikes in the signal that resulted. The effect of these two spikes on the RMS level of the signal will be very small as a result of the averaging that occurs in calculating the RMS value. Now think about bearings. Bearings are precision components designed to have a long service life. When bearings become damaged, usually as a result of some underlying problem such as lubrication faults, misalignment, excessive loads, etc., they do generate impulsive signals. These result from impacts which occur as, for example, raceway defects are overrolled by the bearing elements. Impulsive signals are also generated by the rolling action that occurs between damaged or broken gear teeth. Consider this signal's time waveform. It exhibits some tall peaks due to short duration impacts. Could these be the result of bearing defects? If we use an RMS amplitude descriptor to arrive at an overall value for this signal, then the effect is to average the individual values and reduce the measured level to a much lower calculated value. Individual peaks would have to grow massively before they had an impact on the RMS value. Selecting a peak or peak-to-peak detector would still not capture the data correctly, as instruments calculate these two descriptors from the RMS value. See Module 3, peak equals 1.414 RMS. Peak-to-peak equals 2 peak. Note that some instruments, such as the SKF microlog, offer a true peak detector, which would be the correct selection for studying this type of data. To detect bearing damage in its early stages, a technique is needed that can detect the small impulsive signals that are generated when impacts occur between microscopic flaws in bearing elements. This vibration is typically very small in comparison with general machinery vibration resulting from misalignment or unbalance. So it becomes evident that simply monitoring the RMS vibration level is inadequate for this task. Whilst this is effective for detection of common machinery faults such as unbalance, misalignment and looseness, it cannot be relied on to give early warning of impending bearing problems. Development of SKF's implementation of enveloping, demodulation, was carried out in a practical research environment. No other condition monitoring company has real bearing test facilities such as those of SKF in the Netherlands, India and China. SKF uses the technology of enveloping in their own factories. It was first used in the 1960s as a quality tool. Let's take a look at how enveloping works. The illustration here shows a time domain signal, acceleration, resulting from low-frequency shaft-related vibration. In the illustration at lower left, we now see the effect of the impulsive signals resulting from a bearing defect. The first stage of the process involves band-pass filtering of the time domain signal using a band-pass filter that centers on the region of high-frequency energy. The figure on the right above shows the filtered output in the time domain. The filtering process results in a series of spiky bursts of energy, which are the impacts from the rolling elements hitting the defect as the bearing rotates. Key to SKF's implementation of enveloping, GE, was standardizing on 4 bandpass filter values across all SKF instruments. ENV1, 5 Hz to 100 Hz. ENV2, 50 Hz to 1 kHz. ENV3, 500 Hz to 10 kHz. ENV4, 5 kHz to 40 kHz. The next stage of the process is to pass this filtered time signal through an enveloper in order to extract the repetition rate of the spiky bursts of energy. Historically, the enveloper is an electronic circuit that demodulates or rectifies the signal. In today's vibration data analysis equipment, this process is done using digital signal processing, DSP, enveloping algorithms. The result of passing the signal through the enveloper is shown here in the time domain. Units of measurement applied to the envelope signal are GE, that is GS of envelope. It provides a figure of merit that can be used to reliably monitor change in the condition of bearings and gears. Enveloping can also be applied as a diagnostic tool, and we shall return to this in the Diagnostics module. SKF software is available to aid correct filter selection and to suggest appropriate tolerances. The keys to a successful vibration-based condition monitoring program is consistency in measurement location and in transducer mounting method. Let's begin by selecting our measurement locations. Vibration readings are usually taken at the bearing housings. This is logical because vibration is generated by forces that result from the rotating parts of the machine, and these make contact with the machine structure at the bearings. On this machine there are 4 bearings, 2 on the drive motor and 2 supporting the fan impeller. Enveloped acceleration readings are to assess change in bearing condition, so again it is logical to take measurements at the bearing housings. Where machines include a gearbox, then enveloped acceleration signals generated by gear meshing will also be detectable at the housings of the supporting shaft bearings. General machinery problems such as unbalance, misalignment and looseness will generate vibration in a radial direction. Due to gravity, most machine structures are stiffer in the vertical plane, and so the horizontal plane of measurements is often, but not always, the most responsive to changes. Ideally, enveloped acceleration readings should be taken in the bearing's load zone. However, in most cases this is not possible, and the compromise is to take the readings in the horizontal plane. However, when looseness develops, especially in the machine's mounting, this often causes a vibration increase in the vertical plane. It's common practice, therefore, to take measurements in both horizontal and vertical directions. Misalignment conditions, on the other hand, also generate thrusting forces, and so tend to cause a vibration increase in an axial direction. When you take axial measurements, be sure that the instrument's tip is held firmly against a suitable surface, such as the bearing housing or some other machine face. Where a machine employs thrust bearings, these are taking load in the axial direction, and therefore measurements of enveloped acceleration should also be taken in the axial plane. Many portable instrument systems provide an accelerometer that has a magnetic head with which to temporarily attach it to the machine. Properly used, this does provide better consistency of data than is obtained by hand-holding the sensor against the target surface. Remember, though, that one of the faults that can be detected by vibration monitoring is looseness. If the sensor is loosely mounted on the machine, then we shouldn't be surprised if that fault is detected. Make sure that the magnetic head sits firmly on the target surface. If that surface is curved, then rotate the magnet so that it does not rock. Where it is necessary to hand-hold the sensor, then hold it with a firm, even pressure against the machine surface. Don't press so hard as to dampen out the vibration that you're trying to measure, especially on light, flexibly mounted machinery. Each and every rotating component will produce forces and vibration that relates to the frequency at which it operates, that is, its rotating speed. When we view the overall vibration in the time domain, it is usually very difficult to identify the individual components. However, when we view the signal in the frequency domain, the picture becomes much clearer. We briefly saw this view of the data earlier in the terminology module. The process by which modern digital instruments generate this view of the signal is called fast Fourier transform, FFT. For this reason, people often refer to the spectrum plot or time domain plot as an FFT. If we observe an amplitude increase at a frequency, then we know that the forces have increased and we can diagnose which component inside the machine is at fault. A common way of using this data is to use the baseline technique. The baseline is the spectrum from a machine in acceptable condition. When the monitoring process indicates that significant change has occurred, a new spectrum is prepared and compared with the baseline. It's the differences that tell the story. In this example, we can clearly see that it is the high-frequency vibration from the gear mesh that has increased. The gearbox output drives into the driven machine, which could be fan or pump, so there will be forces due to the residual unbalance of the driven rotor. Plus, if it is a fan or pump, the number then add forces at the number of blades times the rotor speed. The rotors of the motor, gearbox and driven machine will all be supported by at-rolling elements, bearings, all generating forces at which the rolling elements spin. In short, every single moving component will generate forces at the speed of their motion to result in multiple excitation frequencies. The time domain trace for a complex waveform is difficult to interpret. However, with the aid of a spectrum analyzer, we can break the complex waveform back into its constituent sine waves. As was explained earlier, the process by which modern digital instruments perform this analysis is called fast Fourier transform, FFT. For this reason, people often refer to the resulting display as an FFT. There is no black art to interpreting a spectrum. Armed with the knowledge of the rotating components that make up the machine, and knowing their rotational speed, tells us where to look in the spectrum for an increase in vibration due to a developing fault. The impulsive signals generated by bearing faults are repetitive and predictable. For example, the frequency with which a rolling element passes over a defect in the outer raceway is simply a function of bearing geometry and shaft speed. Each bearing component has a unique defect frequency which enables a specialist to pinpoint damage. The following defect frequencies can be calculated. BPFO, ball roller pass frequency, outer ring raceways, Hertz. BPFI, ball roller pass frequency, inner ring raceways, Hertz. BSF, ball roller spin frequency, Hertz. FTF, cage frequency, fundamental train frequency, Hertz. A program to calculate bearing defect frequencies and thereby pinpoint damage is available online at www.skf.com/bearings. We can also view envelope signals in the frequency domain. Earlier we looked at an envelope signal in the time domain. This clearly shows the regular repetition of the impulses with respect to time. We can see that there is an impulse every x seconds. If we view that signal now in the frequency domain, we can now see the repetition rate of the impulses, that is the number of impulses per second or impulses per minute. This makes it easier to relate the signals to the expected fault frequencies and their various harmonics. In the case of bearings, of course, we are not often concerned with whether the fault is, for example, on the inner raceway or outer raceway. However, the ability to be so specific aids confidence in decision-making, especially if the decision to take a machine out of service has significant operational implications. This is also useful when the readings come from a gearbox. It becomes possible to discriminate between a bearing fault and a gear problem. To illustrate the power of enveloping to detect gear mesh signals, the upper trace shows the 10 kHz velocity spectrum from a crane gearbox. It is almost impossible to see the gear mesh frequency. The lower trace shows the 1 kHz enveloped acceleration spectrum from the same gearbox. The gear mesh frequency is prominent along with harmonics.